Hi, in this video we're going to look at question 5 from the Maths Admissions Test from 2018 for admission to Oxford University, Imperial and Warwick. Please do like the video and subscribe to the channel if you're finding these useful, and there are links below to the playlists for all of this paper and for the questions I've done from the 2016 and 2017 papers, as well as a link to my Amazon shop with some recommended reading and other things that you can get there. Well, let's get on with this video. Question 5 is the last one that maths applicants do, but everyone answers this question. There's also 6 and 7, which I will do for this paper for the computer scientists, but everyone does this one, and I really enjoy these questions. They look a bit less like A-level maths questions. Maybe there's beginnings of what we might think of as maybe discrete maths, but they feel like a bit of a problem-solving kind of puzzly sort of question. Might sort of, they feel kind of sort of purer logic problems than the others that rely more directly on A-level maths. Now, usually then that means that you have to spend a little bit of time just getting your head around what the question is asking. Okay, so let's do that here. So it says let n be a positive integer. An n brick is a rectangle of height 1 and width n. Okay, so an example of an n brick here, I've got a 3 brick, a 4 brick, a 1 brick. So this picture here is made up of different bricks. Now it says then a 1 tower is defined as a 1 brick. Now this is a very typical mathematical definition of something that seems a bit confusing, but it's meant to be just saying, okay, actually this thing that's just a 1 brick, I'm also going to call it a 1 tower, and you can see that so on its own it's a tower. Like this is also going to be a tower, but I could also, but if it's just 1 high, that would be like the smallest type of tower we can have. But then an n tower for n greater than or equal to 2 is defined as an n brick on top of which exactly 2 other towers are stacked. Okay, so for example, this picture of a tower has a 4 brick, and you can then see there are 2 other towers on top of it, right? You've got this 1 tower that we just defined here, and another tower here with these 3 layers. That is then a 3 tower because it's a 3 brick with 2 other towers on top of it. 2 tower here and a 1 tower, and the 2 tower has 2 1 towers on top of it. So now it does specify in the question that the 2 other towers stacked on top have to be a k1 and a k2 tower, such that 1 is less than or equal to k1 is less than or equal to n minus 1. So what in particular what that means I can't do is I can't have a 4 and then another 4 on top of it, right? That's not going to be allowed. At every stage the numbers here have to be smaller than 4, the numbers here have to be smaller than 3, and so on. So as the k1 tower is placed to the left of the k2 tower, so side by side they fit exactly on top of the m brick, but notice, I mean, the k1 and k2, neither of them has to be smaller than the other. Like here I've got 1 to the left of 3, and here I've got 2 to the left of 1, but that's how we build up these towers, okay? So we spent quite a while already just thinking about this question without doing anything, but you really do need to absorb that information before you can go on and answer these questions, okay? And so the first part of the question really here is just to sort of check that you've got the idea. So it says, can we draw the other 4 towers? And okay, so I think it's fine here just to sort of start playing around with what these are going to look like. I'm going to draw them slightly imprecisely, I think. So I've got a 1 and a 3 here. So maybe actually a sensible thing would be to say, oh, can I start just with the same arrangement here? Well, okay, I could just put the 2 and the 1 the other way around. That would be one way of doing that, and then I've got to put the 1s on the top here. Notice the definitions means that once I've got a 1, nothing can go above it because that's a 1 tower. So 1 towers don't have anything above them. So that's one way of doing it here. Okay, now actually, of course, I could then do the same thing with the 4 and do the ones that are symmetrically the other way around. So I have the 1 and the 3 here, and then I can have my 2 and the 1 with a 1 and a 1, and then I could have the 4 with a 3 and a 1, and then I could again put these the other way around, so I could have the 1 on this side and the 2 here, and then a 1 and a 1, and so 4 others, so there's 1 more. Now the only other possibility is that rather than having a 1 and a 3, I could have a 2 and a 2, and then actually the only thing that can happen once I've got a 2 is that I have a 1 and a 1, so it must look like this. And there we go, we've got all the others. And it tells us there's only 4, so even if I wasn't convinced by logic that I've got them all, the question tells me that I have. Okay, oh by the way, some people ask me, how important it is to do these things neatly, and I think what I've drawn here, okay, you do it slightly more neatly if you weren't writing with this pen that I'm using here on a tablet, but you don't need to do these perfectly neatly with a ruler, and that sort of stuff, as long as it's, unless you are very, very bad at drawing things neatly by hand, like this one on the left here I'd be perfectly happy with. I'd maybe want these ones slightly neater, but actually everything I've got here has got the structure of the answer. You get full marks for presenting it like that. So you don't have too much time in this exam, so you've got to get on and do the mathsy bits. Okay, what's the maximum height of an n tower? And then justify your answer. Okay, again, you have to spend a bit of time thinking about this, maybe playing around with it. But if we look at our answers here, one thing we can see is that actually having the 2 and the 2 made for a shorter tower than in the other cases. And in these ones where we had the maximum height towers, you see at every stage I've got a 1 and something else. And then from the 3 I've got a 1 and a 2. From the 2 I've got a 1 and a 1. And if you think about it, that's just the maximum that you can have. Because at every layer, right, the largest number has to go down because of this n-1 criteria, right? So if I start with 4, on the layer above, the largest number I can have is a 3. Then on the layer above, the largest number I can have is 2, and then a 1. So the way of getting maximum height is to make sure I include all of those numbers and don't skip any, right? So I clearly can't have something more than height n for that reason, and n is attainable by just creating a tower that if I start with n here, whatever that is, I can have n-1 and 1, and then n-2 and 1, all the way up until I get to something that's going to have a 2 and a 1, I guess, and then a 1 and a 1, and that's the end. Okay, so so you should also write something in words here to that extent. This diagram here shows that n is always possible, and also it must be less than or equal to n, because each layer has the largest brick smaller than the layer below, or something like that. Okay, so I haven't written this very neatly, and this is actually a case I think where you should probably write a few more words to explain what I was saying in the run up to that. But that's the idea. Okay, the maximum height of an n tower. I suppose I should actually make sure I give the answer somewhere here as well, that it is n, and that's that. Okay, so question 3, the area of a tower is defined as the sum of the width of its bricks. For example, the 4 tower drawn above, and I've just copied the one from the question here, as area 4 plus 4 plus 3 plus 2, because we're just adding up the total of all the numbers here in the picture. Okay, so give an expression for the area of an n tower of maximum height. Okay, so actually if I just take that picture that I've drawn there, and let's copy that into this page. So you can see from this structure that the area, okay, I've got, and there's different ways you can add this up, but I think the easiest way is to look at it and say I've got all of these 1s, okay, and how many of those are there? There are n-1 of them, okay, because the bottom row doesn't have one, but every other row does. And then apart from that, you've got 1 plus 2 all the way up to n, right? So it's n-1 plus 1 plus 2 plus 3, etc., all the way up to n-1 and n. Okay, and this thing here is the nth triangle number, or you can, if you want to, think of it as the sum of an arithmetic progression that goes from 1 to n. Okay, so this is 1/2 times n times n plus 1, just using that knowledge that you have about either triangle numbers or arithmetic progressions. And now if I multiply this out, I get 1/2 n squared plus 1/2 n plus n minus 1. So I can simplify this to get 3/2n, and that will be a good final answer. Part 4. It says, show that there are infinitely many n such that there is an n tower of height exactly 1 plus log to the base 2 of n. Okay, so now this might take a little bit of thought. I mean, I've got log to the base 2 of n, so I'm in the mindset of powers of 2. You might even just want to remind yourself what this means to help you think about this clearly. If k is log to the base 2 of n, then that means that n is equal to 2 to the power of k. So in fact, that's a good place to start. So let's assume that my n is 2 to the power of k, and think about how I can always draw a tower from this n, which is 2 to the k, right? Because if it's exactly 2 to the k, that means I can draw a tower a little bit like in my first question that looks like this, where at each stage the width is halving. Okay, so the next one, okay, I'll split it into n over 2 here and n over 2. So actually, if the height of if this one is 2 to the k, then this is 2 to the k minus 1, and I can just keep subdividing into 2 here, right, until eventually I get to some point at the top. Because it's a power of 2, I must end up with the last 2 layers up here, where okay, I can't draw this too well here, but the widths, okay, yeah, the widths, all of these ones are 2 bricks and these are 1 bricks. Okay, so this is 2 to the 1 and 2 to the 0. Okay, so I can actually draw here a good, fairly convincingly, if you accept what's going on with these dots here, that if I start with a tower where n is 2 to the k, then I get all of these layers. Now, how many layers are there here? There's 0, 1, all the way up to k, right? So this tower has k plus 1 layers, and now of course k was log to the base 2 of n, so that's 1 plus log to the base 2 of n is the height of this tower. Okay, so we're actually done, right? Because I can do this for any k, right? Okay, so I think maybe we should make this really clear. So there are infinitely many such towers, because you can just take any k, from 1, etc. Infinitely many possibilities here. Then we can construct a tower like this. Then construct a tower with n equals 2 to the k as above. Okay, and I can do that I can't do it for any n necessarily, but any n that is of the form 2 to the power of something, so 1, 2, 4, 8, 16, etc. Then we'll be fine. Okay. Part 5 says write Tn for the number of n towers there are. Okay, so we know that there's only one n tower, only one tower, sorry, just the single block 1. Okay. And in fact, I suppose we also know, if we think back to question 1, that there are 4 towers, so perhaps I also know that T4 is going to be equal to 5. But it says for n equals 2, give a formula for Tn in terms of Tk for k less than or equal to n. Okay, so I mean, you might start playing around with this a little bit before you jump into a formula. I can think of 2 towers. Actually, there's only 1 2 tower as well, so I've also got that T2 is 1. you could probably do the 3 towers without too much trouble as well, right? Because for a 3 tower, I've just got to do either 2 and 1 like that, or I can do 1 and 2 like that. So actually, there are only 2 3 towers. Okay, so I've got, you might start looking to see if you can find any patterns in these things. 1 1 2 5, and it's not totally obvious here where this is going, but I think drawing these out helps you start to frame your thoughts. Again, you can look back to question 1 here, right? And what I can do is I either put a 1 and a 3 and then build towers on top of that, or a 3 and a 1 and build towers on top of that, or a 2 and a 2 and build towers on top of that. Okay. And so if you think about it, that's what we'd have to do for sort of any larger number here, right? So if I'm starting to think about T5, I'm not going to try and draw them all out, but for the first layer on top of a 5, I'm either going to have to do 1 and a 4, okay, or I might have a 2 and a 3, or I might have a 3 and a 2, or I might have a 4 and a 1, okay? And then how many of each type are there, right? Well, okay, there's going to be how many are there of this type? Okay, well, there's T1 1 towers and T4 4 towers. So of this type, I could take any combination for here for 1s and any combination for 4s, and I'd multiply those together. Okay, here T1 is just 1, so this is just T4. But in general, how many are there of this type? Well, there are T2 of this type and T3 of this type. So I could take any type of T2 tower with any type of T3 tower, and there would be T2 times T3 of them. Again, actually, because T2 and T1 are just 1, actually, you can simplify these, but in general, this formula is going to work, and that's why I'm writing it out like this. So this is T3, T2, and this is T4, T1, okay? Right, so actually, for T5, what I want to do is do T1, T4, plus T2, T3, plus T3, T2, plus T4, T1. Okay. Now, if you can show the structure here clearly, you might get the marks, but it does want something in general for Tn. Okay, so I've got to really try and pick this apart and think about what I'm doing. Okay, so actually, one way to write this down would be using sigma notation for sums, and I could say it's the sum from, let's start at k equals 1, and I'm going to do tk, and then I'm going to do Tn minus k. Okay, so for 5, if k is 1, n minus k is 4, and then if k is 2, n minus k is 3, etc. Right? And then I stop after n minus 1 terms here, so we finish when I get to n minus 1. Right, and this is a nice general formula, okay, for Tn. Now, so I have to work this out for T6. Okay, so actually T5 we have to do first is T1, T4, which is, I've got to be careful now, 1 times 5, so that's 5, plus T2 times T3, so that's 1 times 2, which is 2, and then plus another 2, plus another 5, so I think I get to 14 here, and let's add that to my little table up here. And then finally we'll do that for T6, okay, which is going to be T5, T1, plus T4, T2, plus T3, T3, plus T2, T4, plus T1, T5. And notice I'm getting some repetitions here, like T5, T1 and T1, T5 are the same thing, and that's going to be something that will be useful to us later. So this is 14, T4 times T2 is 5, T3 times T3 is 4, and then okay, I get another plus 5 plus 14, so I've got 28, 38, 42. Okay. So hard maybe to write this down in general, perhaps, depending how much you've done series and thought about these sort of slightly different kind of series rather than just arithmetic and geometric progressions. But even if you didn't write this down, you could perhaps still find the structure and get to get to T6, okay, and get most of the marks. Right, so that final part says show that Tn is odd if and only if T2n is odd, and this is really where we're going to have to use that structure about the duplication that I was saying here, that we get the T1, T5 appearing twice, but you see when you've got an even number here like T6, you only get T3 appearing in one of the terms, but you get everything else appearing in two of the terms. And for any even number, that's going to be the same, because there's going to be this one in the middle on its own, and that's really going to be key here. Okay, so I'm going to write this down formally, and you should, in the real exam, try and write it down as formally as you can. But of course, just try and write a convincing argument. So I've written this as the sum from k equals 1 to 2n minus 1 then of tk times t2n minus k. Okay, so that's just exactly the formula that I wrote down before, but instead of n, I've now got 2n, because I'm looking at t2n. And now I'm just gonna now say that by what we've noticed before, right? This is two lots of t1 times t2n minus 1 plus t2 times t2n minus 2, etc. Okay, so it's 2 plus all of these, and the last one of this type, if you think about it, would be tn minus 1 times tn plus 1. Okay, so we haven't quite got to half of 2n, which is tn. That'll be the last one of those terms, and then on its own I'm going to have tn. So now we also know that if tn is odd, in fact I can say a slightly stronger statement here, tn is odd if and only if tn squared is odd, right? We know that odd numbers square to give odd numbers and evens square to give even numbers. And the structure we've got above here is that t2n, okay, is equal to an even number, right, which is this bit here, which is even because it's 2 times an integer, okay, plus tn squared. Okay, so that means that t2n is odd, okay, if and only if tn squared is odd, okay, because even plus an odd is going to give us an odd, but even plus even would give us even, and that's true if and only if tn is an odd number, and actually that's what we were required to show. Okay, so basically we're saying if you look at something like T6, right? Okay, I've got 14 plus 5 plus 5 plus 14. You add those together, that's going to be even because I've got two lots of each of those numbers. And so whether this number is odd or even just depends on whether this number is odd or even, right? And this number is T3 squared. So if I took the square root to get back to T3, that would also be even. Okay, so if that number was even, this would be even, and then that makes the whole thing even. Whereas if this is odd, then this one is odd, and then this whole thing would be odd. Okay, and that's true, of course, just for these even powers, because for the odd ones, t2n plus 1, i.e. 2, and the odd powers, well, actually they're all even because they're always going to, well, apart from t1, of course, but they're always going to split up into like a 1 and a 4 and a 4 and a 1 and a 2 and a 3 and a 3 and a 2, so that they all have pairs. Okay, right, I hope that makes sense. That's the end of this question. They're meant to get hard by the end. It's a tough logic problem here to get the answers and also to explain it really clearly on paper, which is why it's a good idea to practice a few of these papers before you go into the real one. And hopefully you find this useful. Please do like the videos and subscribe to the channel. Have a look at the other ones in the playlists that I've made that I'll link below. Have a look at the Amazon store for some recommended reading, also linked below. And as I say, at some point I'll do questions 6 and 7 for the computer science applicants. Also, good things to practice if you've done all the other ones and you're applying for maths. And please put in the comments below anything else you'd like me to do. Let me know what you're up to, and I will see you in the next video.